Greetings, folks. A motional EMF is an electromotive force that's generated when you have a coil either move into or out of a region in which there exists a magnetic field. We're going to look at that situation in this video. So here we have a region in which there exists a magnetic field. The magnetic field is into the page. Here we have a coil. I've made it rectangular just for ease of use. And the coil is moving to the right with a constant velocity. When the coil finally moves into the magnetic field, stuff happens. Specifically, the coil begins to experience an increase in magnetic flux through its face. The changing flux induces an EMF in the coil, with Faraday's law making that EMF calculable. Noting that the magnetic field is constant and into the page, and that assuming that the number of winds is 1, we can write the magnetic flux expression as magnitude of B, magnitude of A, cosine of the angle between those two. If A is assumed to be into the page, which is the same direction as B, that angle is 0, the cosine of the angle is 1. So we have the induced EMF is minus B, which is a constant, which we can pull out, times the change in the area with respect to time. If we started the clock when the coil was just outside the region and assumed that it moved a distance x in time t, the initial area in which there was magnetic field impinging would be 0. The final area in which there would be a magnetic field impinging would be h times x, hx. So the change in the area would be hx minus 0 divided by the time interval. And if you notice that h is a constant, which means you could pull it out, so you have minus b times h, and the distance traveled x divided by the time is just the velocity, you end up with this relationship here for the induced EMF. There is a more elegant way of doing this with calculus. If you simply determine what the magnetic flux is, which is B times the area h times x, then notice that the induced EMF is just the derivative of that. You can pull out the constants, work your way down to the time derivative of the position function, which is just the velocity, and end up with the same relationship that we got on the previous page with less pain. Anyway, the EMF generates an induced current. And according to Lenz's law, the induced current generates an induced magnetic field of its own through the face of the coil. In this particular case, that magnetic field is going to end up being out of the page. So as a quick review, how do you decide whether that induced magnetic field is out of the page or into the page, and how do you use that information to determine whether the induced current is clockwise or counterclockwise? And the technique that I've given you is as follows. This is just a summary. Step number 1, you identify the direction of the external magnetic field. In this particular case, the external field is into the page. Step number 2, if the magnetic flux had been decreasing, which didn't happen to be the case in this instance, but if it had been decreasing, the induced magnetic field that was set up here due to the induced current in the coil, that induced magnetic field would be in the same direction as the external magnetic field. In fact, we went from no magnetic flux to some magnetic flux, which meant the magnetic flux was increasing. In that case, the induced magnetic field, which is going to be in here, is going to end up being opposite the direction of the external magnetic field. So the induced magnetic field is going to be out of the page. Once we've determined the direction of the induced magnetic field, all we have to do is use the right-hand rule to determine what direction the current had to be to generate that magnetic field. And to do that, you would simply use the right-hand rule. Notice that the thumb here is pointing upward. You can see the thumbnail. It's pointing upward because the induced magnetic field you've decided has to be upward. The fingers of the right hand are curling in the direction of the induced current. And so you have a counterclockwise current in this case. The magnitude of that current can be determined using Ohm's law. Presented here, all we have to do is substitute in the EMF, divide by the resistance, and we have the induced current. So back at the ranch, as the coil moves into this magnetic field, it generates an increasing magnetic flux, which induces an EMF, which induces a current, which in turn produces its own magnetic field through the cross-section of the coil. What's interesting, though, is that along with all of that, you end up with a current-carrying wire in an external magnetic field. And that's going to end up feeling a force governed by IL cross B. So if you take L and you cross it into B, you will end up with a force on this current-carrying wire. And doing that cross product uncovers a force that is in a direction such that it's fighting what you're trying to do. You are trying to push this coil into this region in which this magnetic field exists. This induced current is creating this induced force on that current-carrying wire that's making it harder for you to do that than would otherwise be the case. The magnitude of that force can be determined using IL cross B. We know what I is because we just calculated it. L is the length of the wire, which is H. B is B. The angle between L and B is 90 degrees. We end up with a force equaling B squared H squared V over R. So as time proceeds, the coil continues on into the magnetic field. Moving at a constant velocity, the flux continues to change at a constant rate, which means the induced EMF stays constant. The induced current stays constant. And as a consequence, this retarding force stays constant. Once the coil gets completely into the magnetic field, there is a magnetic flux through the coil, but it's not changing. And because there's no change in the magnetic flux, there will be no induced EMF, which means there will be no induced current, which means there will be no magnetic forces acting on the coil in this region, which means it can move around in the region freely. After a time, it will finally get to the point where it tries to exit. When it does that, you will have a decrease in the magnetic flux. According to Lenz's law, this will produce an induced magnetic field that's in the same direction as the external field. And using the right-hand rule once again, with the thumb pointing into the page, the fingers of your right hand will curl in such a way as to identify an induced current in the coil in a clockwise direction. Using IL cross B once again to determine the force on this induced current, you're going to end up with a force that is, just as before, fighting what you're trying to do. In this case, you're trying to pull the coil out of the magnetic field. This force is making it harder for you to do that than would otherwise be the case. So the bottom line is any coil that moves into or out of an external magnetic field will feel a magnetic force that fights the motion. That is, if the coil is pushed into the magnetic field, the force produced by the interaction of the induced current and the coil with the external field will make it harder to do this. And if the coil is pulled out of the magnetic field, the force produced by the interaction of the induced current in the coil and the external magnetic field will make it harder to do this. In short, in all cases, the interaction of the induced current with the external magnetic field will produce a force on the coil that fights the change. That's what the deal is with motional EMFs. So, for the amusement of it, and just to end this whole thing, I'm going to let you see the animation in its entirety. And that, friends, is it.